You know, deep down inside every STM32 microcontroller, there's a clock system. It's the heartbeat, the rhythm section that sets the pace for every single thing the chip does. And look, getting this right, it's the difference between a project that kind of works and one that performs at its absolute peak. Today, we're going to unlock that performance.
So let me ask you something. Is that powerful STM32F4 on your desk actually, well, running at a snail's pace? And chances are, if you've never messed with the clock settings, the answer is a big yes. Right out of the box, these things wake up in a safe, slow mode. They prioritize just working over raw speed. But that incredible potential, we're talking up to 180 megahertz, it's just sitting there, waiting for you to unleash it.
So, here's what we're going to cover. First, we'll talk about why you'd even bother changing the clocks. Then we'll look at the MCU's default state and map out the entire clock tree. After that, we'll walk step by step through the high-speed configuration sequence. I'll show you how to avoid the most common mistakes, and we'll wrap up with the key takeaways.
All right, so first up, why should you even care about any of this? I mean, why not just leave it at the default settings and call it a day? Well, the answer really boils down to what you're trying to build. I mean, think about it. If you're doing any heavy lifting, like complex math or digital signal processing, cranking the CPU up to its max speed is a no-brainer. Your code just runs faster. Simple as that. But it's not just about speed. High-speed stuff like USB or Ethernet, they have super strict timing needs that the default internal clock just can't handle. Even something as common as UART needs a stable clock to get reliable baud rates. And then you have peripherals that are just plain demanding. The USB controller, for example, flat out needs a perfect 48 megahertz clock. The defaults just won't cut it. Okay, so to figure out how to speed things up, we've got to know where we're starting from. Let's take a look at what's happening inside that chip the very instant it gets power. And you know, there's a really smart reason for this. The folks who designed these chips wanted to make sure your microcontroller could start running your code immediately, no questions asked, without needing any external parts. That's why it always defaults to the high-speed internal oscillator, or HSI. It's a 16 megahertz clock source that's baked right into the silicon. Now, it's not super accurate, but it's dependable, it starts up instantly, and it guarantees your code runs right out of the box. So this leads us to our first big decision. Stick with the internal HSI or go with an external crystal, the HSC. The HSI is great. It's free, it's built in, it starts fast. But its frequency can drift with temperature and it's only accurate to about 1%. That's totally fine for a lot of things. But the HSE, that's your high precision option. It uses an external crystal, so it's incredibly accurate and stable. The trade-off? It costs a bit more, needs a couple of capacitors, and it takes a moment to stabilize. The bottom line is, for anything that needs precise timing, HSE is the way to go.
All right, so we've picked our clock source. Now what? How does that little pulse get all the way from the oscillator to the CPU and all the other peripherals? Well, for that, we need to look at the clock tree. Just think of it as the plumbing diagram for all the timing signals inside the chip. So let's follow the signal's journey. It all starts with our source, either HSI or HSC. That signal gets piped into something called the phase-locked loop, or PLL. Now, the PLL is the real powerhouse here. It multiplies that frequency way, way up. After the PLL, we hit a multiplexer, which is basically just a switch that lets us choose our main system clock, or SYSCLK. And that SYSCLK is what drives the CPU core, the memory, and after being divided down a bit, all of our peripherals. So let's be super clear here. The PLL, that's our magic bullet. It's how we smash right through the speed limit of our little crystal oscillator. It's a frequency synthesizer. It takes a nice, stable, kind of slow input, like our 8 megahertz crystal, and through some electronic magic, it generates a super stable, super high frequency output, like 168 megahertz. This is the key to getting max performance. All right, now for the part you've been waiting for. Configuring the clock isn't just about flipping random bits on and off. No, it's a very precise, very ordered sequence. You have to do things in the right order, and getting it right is everything. So here's the game plan, high level. First, we turn on our external crystal, the HSE, and we wait for it to get stable. Then, and this is super important, we tell the flash memory to get ready for a faster clock. After that's done, we set up our PLL dividers, turn it on, and wait for it to lock. And finally, after setting up our bus speeds, we make the big switch and tell the system to start using our shiny new PLL clock. Let's dig into each step. First things first, assuming you're using an external crystal, you have to turn it on. But you can't just power it on and move on. Crystals take time to warm up and stabilize. And I can't stress this enough. Your code absolutely has to just sit there in a loop, checking that HSERD flag until the hardware tells you it's good to go. Skipping this wait is the #1 reason clock setups fail. Full stop.
This next step is so important, and you have to do it before you speed everything up. Think of it like this. Your CPU is suddenly working at lightning speed, but the flash memory where your code lives is still moving at its old, slower pace. If the CPU asks for the next instruction and the memory isn't ready, what happens? Chaos. So we add wait states. These are just tiny intentional pauses that give the flash memory time to catch up. If you speed up the clock without adding wait states, your system will crash. Guaranteed. Okay, time to configure the PLL's gears. Seriously, just think of the M, N, and P dividers like a gearbox. The M gear divides your input clock down. The N gear multiplies it way up, and the P gear divides it back down to the final speed you want. Now, the golden rule here is that the PLL has to be turned off before you start changing its settings. You can't change gears while the engine is redlining, right? Same idea. Let's walk through a real example to make this stick. Let's say we have an 8 MHz crystal. We'll set M to 8. That divides our 8 MHz down to 1 MHz, which is a perfect input for the next stage. Then we set N to 336. That multiplies our 1 MHz all the way up to 336 MHz. And finally, we set our P divider to 2, which cuts that in half and gives us our beautiful final system clock of 168 MHz. See, it's just a little bit of math. So once our gears are set, we fire up the PLL by setting the PLL on bit. And yep, you guessed it, just like with the HSE, we have to wait. We sit in a loop and check the PLLRD flag until the hardware gives us the thumbs up that the PLL is stable and looked. Only then, only when everything is perfectly ready, do we make that final switch by changing the SW bits to make the PLL our new system clock. You know, getting the sequence right is half the battle. The other half is avoiding the common traps that trip up so many people. Getting caught in one of these can mean hours of pulling your hair out, so let's go over them. Now, we've hit on a few of these already, but trust me, they're worth saying again because they cause so much grief. Number one, hands down, is not waiting for those HSDRD or PLRD flags. Right behind it is getting the flash latency wrong. That's a guaranteed hard fault. After that, you've got to check your math and make sure your internal PLL frequency is within the valid range. And remember, you can't reconfigure a running PLL. Finally, a subtle one. Always modify registers in a single atomic operation to prevent weird issues with interrupts.
Whew. Okay, we've covered a ton of ground here, from why we care about clocks all the way down to the individual register bits. Let's boil it all down to the absolute must-know takeaways.
Look, if you walk away with anything today, let it be these 4 things. 1. The sequence is everything. Follow the steps in the manual exactly. 2. Always wait for those ready flags. They are not optional. 3. Set your flash latency before you crank up the speed. And 4. Do the math. Make sure your PLL calculations actually work and don't push any frequencies out of their allowed range. Okay, so now that you've seen how it all works under the hood, I really recommend checking out the STM32 CubeMX tool. It has this awesome graphical clock configurator that does all the math for you and prevents a lot of simple mistakes. After that, you can start digging into some of the more advanced stuff like the special clocks for audio peripherals or the clock security system, which is a cool feature that can save your bacon if your external crystal ever fails. So there you have it. You now have the keys to the kingdom. You can tune the very heartbeat of your microcontroller for insane performance, for super low power consumption, or for the kind of precision timing that complex peripherals demand. The power is literally at your fingertips. So the only question left is, what are you going to build with it?
If you like this one, the YouTube algorithm says you're gonna love my other videos, so go check them out.